Yeah. All right. So this is day 2 of the HamSCI workshop. This year's theme is the weather connection, and so it's really our invited speakers that are driving that theme, and I'll be introducing them shortly. While we're waiting, though, I'll introduce Jim formally in a minute. And Jim, why don't you tell us once again where you're located?
Well, I'm just outside Norwich in East Anglia, which is the eastern side of England, the bit that points out into the North Sea, and about 100 miles northeast of London. So very much on the eastern side of the country, and enjoying a lovely spring sunny. Well, it's an afternoon now, but it's gorgeous out there.
That sounds so nice. And this is one of the really nice things about the that I think we've come across with the Zoom, is that we've been really able to take advantage of all these international speakers that normally would not be able to come. So this is really great. As we get into this, you know, the invited tutorial, let me explain a little bit of the thinking about the way the HamSCI workshop is set up. There's a lot of thought that goes into why we do things the way we do. So HamSCI really is trying to bridge that the communities, the professional community and the amateur communities together. And each of those communities have slightly different traditions. So in the professional research world, you often have these rather fast-paced oral presentations. And that's what we do on Friday. The other thing in the professional world is most of the professionals will attend meetings that go from Monday through Friday because they're working, but amateurs may not be able to because they're working their other jobs. So Friday of the HamSCI workshop is typically formatted more like a professional oral presentation type of meeting. On Saturday, it's supposed to be a little bit more fun and a little bit more community oriented, you know, with the kind of amateur spirit to it. So that's why Saturday is a little bit more, you know, especially if you're here in person, we're going to have a chance to just hang out. Really all afternoon is about hanging out, talking with each other about ideas, getting on the radio, those sorts of things. So, and amateurs are typically able to come on the weekends. So that's why this day is set up on Saturday. Along with that thinking, for the invited tutorials on Saturday morning, we always have 2 speakers, and I typically like one person to represent the amateur radio community, so get someone who's a well-known amateur, and one person to represent the scientific community, get someone who's a well-known scientist, and each give their perspective on things. Now, as Bob McGuire pointed out last night, he said, you know, those 2 communities aren't actually mutually exclusive. So there are many people who are both amateurs and scientists. And perhaps today is one of the days that we really do have someone that kind of, each person sort of represents both communities. You know, we have Jim Bacon, who is a meteorologist, and we have Tamitha Skov, who is a space physicist, but they are both also amateur radio operators. And so it's really nice that we can have both of those people in some ways represent both communities simultaneously. So with that, it is now 9 o'clock, so I'm going to read Jim Bacon's bio, and I'm going to turn it over to him for his tutorial. So Jim Bacon, G3 YLA, is a well-known retired meteorologist from the United Kingdom and is the recent recipient of the Radio Society of Great Britain Les Barclay Memorial Award to recognize those who have made excellent contributions to propagation research and understanding. Mr. Bacon actively develops the PropQuest website, which provides real-time Sporadic-E probability index, or the EPI, that incorporates the factors of tropospheric weather, atmospheric gravity waves, meteors, wind shears, and atmospheric semidiurnal tides. And now I'm going to turn it over to Jim. So I'm going to stop sharing my screen here and go ahead, Jim, share your screen.
Okay, we're just getting underway here, and we'll go into play mode, which should...
I'm adjusting the screens over here.
There in a second, there we go. Is that going to get it?
And I think I'm going to change the view here so it's...
Oh, there it is. Hidden under the tab. There we are.
That look good to everybody? All right.
Is that looking good?
It looks great, Jim. So I'll turn it over to Jim, who will talk to us about the use of ionosonts and weather models to evaluate an experimental sporadic-E probability index, or EPI. Take it away, Jim.
Right, thank you very much. Well, a very good morning to you all. And once again, I have to say a huge thank you to HamSCI for organising this and inviting me, but also just in the general sense of providing this bridge between the professional researchers and radio amateurs. And the love of science and the love of how things work is always a great motivator for doing things. And I've had many years of being a meteorologist. I retired a couple of years ago, really, but over 50 years of looking at weather charts. And during that time, I've had a lot of prods from people to say, oh, well, Sporadic-E, it's all about thunderstorms. And we get into very quickly a sort of a red sky at night philosophy about Sporadic-E. And people tend to focus on one pet theme that seems to work for them sometimes. And my sort of challenge over the last probably 30 years or so that I've been looking at this has been to try and get behind that with a bit more resolution to see just what is going on. So it's a huge debt of gratitude I have to HamSCI, particularly to Nathaniel and Phil and to the two Bills who've been involved in getting me here today. And I find it such a rewarding experience. Yesterday, it was full on 100% absorption day. Just such a great array of talks, and looking forward to going through those when I have a bit more time and studying them again. And in particular, Chris's talk on my street, because it's a Sporadic-E link, of course, and know Chris very well, but also the talks about the Parlap system and the Python version of that. Very intrigued by that. Okay, well, we don't have a lot of time in this. I know I've got a bit more time than you had yesterday, but it still feels like we're pressured. But I'm going to press on and just set out what we have here. But basically, what I'm trying to do is to talk about getting some way of combining what is such a complex thing, Sporadic-E, over the years of looking at it as the layman looking inwards. It just appears that every time you open a paper, you see a reference to something. You thought, oh yes, I've got to add that in. So about 10 years ago or so, I came up with this idea of sketching out the various parameters. But there's far too much here to put into a talk like this. And this isn't about Sporadic-E per se. This is more a discussion, I hope, about why some weather things might be of more interest to us when trying to consider how Sporadic-E happens where it does. This is much more about the why and the where it happens than the ionospheric physics of Sporadic-E itself, which there are many watching and present who have huge depths of knowledge in that area, and I'm sure we're going to hear more about those later on as well. So the bit at the bottom is the weather bit where I live, and things in the weather domain, such as mountain waves, jet streams, thunderstorms, upper ridge patterns, all of these things have had that pointy finger of Sporadic-E, it's all about this. And then the other thing that came into being when I started to dig into it more was the control of the semi-diurnal tidal wind regime in the E region, which has a pattern which fits very well with the two windows we see during the day of Sporadic-E, a morning event and an evening event. So I'm going to look at those linkages, and there's a whole bunch of other things there you see in the middle of that schematic, which there just isn't time to talk about, but you'll almost certainly have been aware of them and will be able to reference articles about them. But it does point to a really rich vein of interest for amateurs. The one thing that happens here that quite appealed to me at the beginning was that amateurs have the advantage of the breadth of coverage in a global sense. So we have a huge array of data sets. The professional researchers are, of course, doing some huge, big infrastructure projects with fixed locations, and they come out with a lot of really valuable science for this. But sometimes just looking at things on a day-by-day basis is just incredibly revealing. So I've approached it from that angle. But a lot of the initial thoughts behind this do depend upon the work of those professional research institutions, and I have to say some very good papers from the recently demised radar, which are just so sad to see the destruction of that. And hurricanes and weather have influences in all sorts of ways, but that was just a tragic thing. So it's with big gratitude to the work that they've done. Anyway, weather bits, which is where we come in. Part one, I'm going to look at something that I've done with ionosonde data. In the weather world, we tend to look at data regularly and look at differences from one day to another. And it's that difference that allows you to understand more about what drives things. And ionosondes we tend to look at as a single image and as a single time, usually, of an ionosonde profile. And it occurred to me we could perhaps visualize things on a more sort of routine way and gain something from that. So that was part one, which we'll talk about in a moment. Part two is how that led on to developing this ease probability index. So I have to say the ease probability index is about a probability of a location in a place rather than the ease will or will not happen. So it's more about the where. And part three is just holding my hands up and saying, fair cop, there are things here which are really difficult to pin down. And because I've only just finished developing some Python programs to review this, I'm stuck with looking at the most recent set of data I have with the full data set, which is February. And February is a very noisy, poor Sporadic-E month. So we'll see what we can make of it at the end. So the first part then is to look at the role played by the tidal wind regimes, which can be hopefully revealed by regular inspection of ionosondes, and that's what we're going to do. So firstly, a brief note about the schematic here, which shows the wind shear part of Sporadic-E, which I won't go into in detail, but it's where opposing wind, neutral winds in the E region can converge ionization produced by meteor input, the ablation of meteors as they burn up. And that has the effect of focusing the ionization into a dense enough layer that makes a Sporadic-E patch. And with time, because of its property as being a gravity wave, it produces the nodes descend with time. Now, my apologies to all those who, of course, know all this and work in it professionally. This isn't meant to be explaining how this works to you, but it is to make it a broader interest point for others who aren't perhaps aware of how Sporadic-E seems to work. And the idea that this descending node is a very important one. But there is also the idea that we need a link with the weather, and another source of gravity waves in the atmosphere is from weather systems, and that turbulence in a weather system can propagate up to the E region. So in its basic form, Sporadic-E forms at a great height, rather enthusiastic arrow here, but I've done a large arrow so that hopefully you can see it from the back of the room. It's a descending node, and then it appears to level off at around about 100 kilometers. So you can see there's a huge change in height early on, and as the intensity of the FOEs increases, it tends to converge on a fixed sort of level. So this descending wind shear node turns out to be really important. So when you look at the time window that this happens, you've got two opportunities a day. It turns out that the semi-diurnal tide is an important one, and it can be picked up in these ionosonde readings, and that kind of fits in with the morning and the afternoon, late afternoon, evening window, when we normally associate Sporadic-E. Well, that you might think is a great result, but of course, if that were the only part to this story, you would then expect that there are two openings every day, everywhere rather. So there's no geographical focus to this, because the semi-diurnal tides are determined by the side of the planet which faces the sun, and as the Earth rotates, that part is heated. It alters the balance of mass in the atmosphere, and you get wind regimes that change on a semi-diurnal basis. So it's called a tidal wind because it repeats with the rotation of the Earth. So how can we bring in something that makes Sporadic-E sporadic in a geographical sense? Well, this is where the weather generated gravity waves come into it. And these are things which are really fundamental to it. We can affect it twice. Anytime there's Sporadic-E around, you've got the tidal component of the converging node, plus you've got this interaction, this modulation of it by a shorter period gravity waves from a weather system. So it's really interesting to look at this. And to separate it out, the sort of signals we're hoping to be playing with, I thought as an amateur sense, would be to see if we can pick up signs of these semi-diurnal tides, the nighttime one, the daytime one. And there is another one here which sometimes crops up, but there are others. If you read the papers, there's a great number of these tidal wind regimes there which can have an impact. The other thing is about the lower level. It's where the ionization comes so low that the recombination rates are significant. So you tend not to get high enough ionization to make an easy patch below about, it tends to be about 100 kilometers, but occasionally down to about 90 or so. So this is what we usually look at, the FOEs and the height, the virtual height of the EES layer, Sporadic-E layer. And these are parameters of the regular ionosons that we see. And big, huge thank you to the Lowell Digison database, the database. It's such a fantastic resource for we amateurs and professionals alike, I'm sure. So big thank you to you folk for what you do, making this available. I developed a program which plotted this stuff more regularly because I felt Sporadic-E we tend to assume is sort of there at a level and that's all there is to it. But a nominal height for Sporadic-E I think is probably a bit of a step too far in some senses, because the difference in the skip distance could be quite significant, about 400 kilometers worth of extra skip. And we need to see if we can pick out some of these things on the ionosons. So this was the first result of a program I developed, which, well, quite clearly shows we've got some very obvious, this is the height of the virtual height of the Sporadic-E layer, is the black curve coming down here. So the y-axis goes from 80 kilometers up to 150 kilometers. And then this is the time of day, solar time, in fact, ideally. So this is a UTC time or UT time. So here's our morning tidal descending node, and here's our afternoon and evening one, plus some very useful looking nodes in the middle here, descending periods. So interesting to see what they might be. But also I've colored the plot so that the vertical color bars represent a crude approximation for the frequency band available, but approaching this not necessarily from the discipline of pure science, but from the amateur radio perspective of which bands might be open. And when I've looked at the cluster websites, it turns out that for CW and SSB, about 8 times the FOEs gives you a good measure of which bands might be activated. So you can see that there are, towards the bottom end of these periods, some spikes where it reaches 6 meters propagation band. So that's interesting. And then when we spread it out over a year, there's obviously huge amounts of data here. But I took, just to make it a manageable task, I just arbitrarily chose to look at the 15th, the middle point of the month. And in January, you've got a descending node, which produces a 6 meter value opening. And we do get these occasional isolated high intensity openings in the middle of the winter. We have the June one, which is much more typically the Sporadic-E season. And that, well, I mean, it's full of stuff, full of 10 meter stuff, the pale bluey green color. But you can see from the lime color here, 6 meters also appeared on that occasion. And then you get the other months, which I've just isolated here. I'm just going to move my who's looking at it bar out of the way so I can see that's March and November. And you can see there's a node shows up well in November, not so much in March. And also interestingly, if you look at the June one, which we take subjectively to be the peak sort of the Sporadic-E season, the descending node is not actually very apparent. It's a much lighter one. And then we get to the two NAF months, so to speak, February and September. It appears to be all over the shop here with a lot of noise and not much sign of focusing of the semi-diurnal tide. So the question is that bit more a meteor input bit, or is it to do with how the semi-diurnal tides behave? You know, is it some property there we need to look at? The other plot I decided to develop was to use a temporal view of things. So spreading out the FOEs. The FOEs is along the x-axis here, goes from just about just one megahertz up to about 9. And then the height altitude y-axis is the same, 80 up to 150. And you can see, hopefully, from the color coding of these ionosonde values for an FOEs and height of FOEs value, that you've got some material here in green, which is an early morning, fairly scattered approach going on here. We've got sorry, I'm getting too pushy with this thing. We've got in the early hours of the morning, the blue colours along the bottom here, which is a residual bit of, I suspect, the diurnal tide. And then we've got this green stuff that morphs into a reddish colour as it intensifies, gets up to just over 5 megahertz here by late morning. So that's your morning window. And then over the top of that, oh, for goodness sake, over the top of that, these super sensitive keypads, over the top of that, we then introduce an afternoon evening period where we get a descending node that starts off at about 125 kilometers altitude and descends. And really the one thing that stands out here is how these events converge onto a fairly fixed height. And it's usually between 100 and 110 kilometers. Now, the question is how long these periods take to form. So this purple run here, it looks as though we're in the period where from about 1600 through to about 1800, we've got about 3, possibly 4 hours worth there. This morning period, which starts with the green colors here, about 6 a.m. of the earlier tide, that sort of goes from there up to midday. So they can be of different lengths, these periods. And if you look at that spread out through the year, we see again this trend that when you get good ease, you get this very marked focusing on a single height range. And then when you're not so good, you're a bit more scattered. Interesting one in November here, which does produce a good value of FOEs at about 5 megahertz. So middle of the month, remember I took this as an arbitrary date for this study. That's about the time of the Leonids. It's just a bit before it, but not by much. So there could have been a meteor component to that. And then February and September all over the shop, and you can see there's not a lot of convergence going on there. Right, I've realised I'm already way behind the schedule, so I'm going to speed up a little bit. This is now where we look at the ease probability index, which is trying to combine as many of those factors into one figure as possible. And it stems from being able to break it down into a component to do with the weather. So the idea being that the weather controls, in my view, kind of a large part of the geographical location of ease. There's a latitude thing which is affected by the tilt angle of the Earth's magnetic field, the horizontal component, and there are other things that come into play as well. But basically, the weather models are very good at forecasting upper air properties of weather charts, and therefore I've got a weather factor which goes from 0 to 100, which is then operated on by another factor which either gives it a bit of a lift or degrades it. So for example, if we're outside the traditional mid-latitude north-south range for the right tilt angle for the Earth's magnetic field, we reduce that factor and it might become less than 1. If we've got high ground nearby, we might change it to be above 1 because of the greater chance of mountain waves and so on. So the jet stream, vorticity, which is the spin in the air, the change of a pressure pattern. If a pressure pattern is moving, that also comes into it. The convection, thunderstorms, the original thing which sort of pointed to Sporadic-E and weather being linked in the amateur world, kind of feels right, because thunderstorms are a huge source of turbulence and gravity waves and all the rest of it, but many of them will tend to be moving through a region. And my question would then be, if they're moving, do they remain in a place for long enough to propagate the gravity waves up to have the effect to then converge the ionization? So you kind of feel that they may be not as significant as originally thought, and that's something that comes out of things. What happens in the stratosphere between the weather and the E region is important, I suspect, because these gravity waves have to propagate through there. And when you look at, I haven't got the slide in this particular talk, but if you look at the stratospheric winds that I think I've chosen 30 millibars for a lot of the work, the changeover from, as Nathaniel was saying earlier on, this polar vortex, this very strong winter westerly flow to a light or easterly flow correlates really well, probably for all the wrong reasons, but it does correlate really well with the end points of the season, of the Sporadic-E season. And then it was a case that Sporadic-E also seemed to be associated with upper ridges, and I'm not really so confident about that now. I think upper ridges are sort of ridges in the atmosphere where it's sort of tending to high pressure, and you think of it as a sand dune and turbulence on the top of a sand dune as it marches. And I think upper ridges may be useful if they're moving quickly, but they're probably not so useful if they're static, and we'll come on to that in a little while. So the jet stream I've scaled according to the 300 hectopascal wind speed, so tends to be a straightforward relationship. In meteorology, by the way, we treat anything above about 60 knots as a jet stream. Obviously, Sporadic-E doesn't know we've defined it like that. So you've got actually the full spectrum of speeds, and sometimes they're more important than others. Vorticity, this is the spin in the atmosphere. You imagine standing beside a stream that's flowing, and the fastest flow is in the middle of the stream, and you put a stick in that stream laterally across the flow from one bank to the middle. Then the middle going quicker will turn the middle forwards, and the bit near the bank will move less forward, so that imparts a spin. And jet stream has marked vorticity maxima, negative and positive, depending on which side you're on the jet stream. And that seems to be an important parameter to look at. Whether the whole pattern is moving is important. Showers, as I said, locally important, but I suspect not significant in the grand scheme of things, looking at a whole year's worth of data. Stratosphere may act as a filter, and the upper ridge is covered by the vorticity thing. So on an upper air chart, this is what this one is. The faint black lines you see here are the contours of the fixed surface, a 300 hectopascal pressure level. So think of it in crude terms the same as a pressure chart on the television, of looking at the millibars on the weather map with highs and lows and things. And the closer together these lines are, the stronger the wind. So these green shading areas are jet streams with the yellow core above 100 knots. Contour changes I also highlight on the graphs, on the maps, and falling is in red areas, blue areas of rising contours. So this represents where the mass in the atmosphere is changing quickly. You're getting falling contours ahead of an upper trough and rising contours behind it. Thunderstorms can be predicted by weather models. So this is a forecast of where thunderstorms are more likely to be severe and interesting. It's there out of interest. So anyway, that's one version. And then I came to look at where vorticity is. And vorticity is interesting because it has some quite pronounced maxima, very thin ribbons of vorticity, and then around lows, large, more general areas of vorticity, as you see here, but also some quite marked local streams. And some of these streams here, like you see over southern France, northern Spain, may be significant in what we're looking at. So it's worth having a think about those. So the well, you can call them being unkind. We could call them fudge factors, but the ways of adjusting temporarily to get some reasonable values is time of day. That's obviously adjusted to match up with the semi-diurnal tides. Mountains come into it as a topography. So if you're near a mountain range, you're more likely to produce gravity waves. Seasonal factors, well, this is to do with the, partly to do, and it joins in with another one later on, partly to do with the, the stratospheric influence between the troposphere and the E region, but also partly to do with the meteor input, because that's seasonally dependent, and other papers will list some of those parameters, which are very interesting. The dip angle comes into it, so I do an adjustment based on latitude. The KP index, we know, affects things, because if the magnetic field is unstable, it may not converge things quite so effectively. And I'm popping a solar flux index on there as something for the future. Everything I set to 1, and then as I get ideas about it, I have a think about what to really put in there for the next test. So there's loads of things in there which are deemed to be important. So when I worked on the key on 6 meters one day, a station in Sardinia from the UK, you can see here, there's me, and here's the station at the other end. And halfway point, the map projection means it doesn't look halfway, but at halfway point there's a little hotspot there of ease. But don't take these too literally. This is more a general idea, a scope of things. So there have been some remarkably good events which have captured a lot of different directions when you have an opening that affects, say, the whole of Europe. So on that particular day, Roquette is in northeast Spain, and that showed, it's the closest one to it. This is the thing, amateurs can work all over the place, but the ionosondes have to stay where they are. So the nearest one was Roquette, and that shows this descending tidal node in the, this one is adjusted for FT8 values, and the lower one is adjusted for CW. So this is basically the one I was working with. So about 138 kilometers descending slowly and converging into this narrow layer at about 110 kilometers, and some evidence at the low values of this diurnal tide here. So what do we see? We see some very strong signature for the morning semi-diurnal tide, and we see a very strong signature for the nighttime one. And the stronger returns from the ionosonde occurring near the base, where you might expect it's had longer to converge this material together. So this is all very interesting, but even more interesting is when you look at things closely, you see that these hotspots come fairly close to the lowest part of very small duration descending nodes. So are these the weather bits interacting with the semi-diurnal tidal bits that seem to be causing our interest? So had I finished that? Yes, I think I had. So this in May, end of May, sort of really into the high season, we had a morning opening here, these brown colours, which came up to about 12 megahertz for the FOEs. So that got us up into the 4 meters territory. And the afternoon one just fell short, but not by very much. So this was one where the 2 semi-diurnal tides both did their bit during the day. You don't necessarily get that. So now, part 3. This is the bit where I've recently only just finished doing some programming for this, and as Nathaniel and Phil said a long while ago when I was putting this stuff out there, he said, well, what would be really nice is to validate these EPI indices against real data. And that is quite a task. There's a lot of data. So what I've done, I've written a program which allows me to take weather model output for ionosonde locations in the domain that I'm looking at. Mostly they're in Europe, but there's about 3 or so in the United States and 1 in the Caribbean. I've only had a chance to work up a European one at the moment, but this will all follow through with more time. So what do we get? Well, some of these things are quite sort of depressing, but I'm sure all you professional researchers will will have come across things like this before. So February, the first complete month of data. Let me just go back here again. It's the same chart, by the way. The EPI, those of you used to looking at scatter plots will just put your head in your hands at this point. But there is a sort of increase here towards the end. Now, what this says to me is, okay, we haven't got this thing right yet, because obviously we would love to see a single sort of linkage between the EPI and the bands that are active. But some of the factors may not be working properly, and we haven't refined them well enough yet. So this says more needs to be done, but it's not a bust. The velocity of the jet stream is kind of interesting because it shows we get a lot going on when the jet stream strength is higher. But this is kind of a measurement of the jet streams that were there during that month of February. It also is interesting that even low values of wind speed up there at jet stream heights can still be associated with an ease reading. Incidentally, I should just say here, the comment here in blue is that meteorological output from these models is an hourly value. It's a forecast value on the hour. Now, it would be a very fine business world if the highest Sporadic-E FOE's value occurred on the hour. It won't. So what I've chosen to do is to take the highest FOE's value in the hour following the meteorological hour. So the meteorological hour gives me the parameters that may or may not make the gravity waves that go up. In the following hour, I check to see what the highest FOEs is. That's just to explain what that reference there is. So this one is the, I'm going to move the people out of the way here. There we go. This one is the vorticity. Oh, let's just do that. This one is the vorticity. And you can see there isn't really a strong bias in favor of positive or negative yet. And it seems to be any amount of spin is good for the job. Then we come on to wind direction of the jet stream. Now this one contains perhaps more information than we might think. So we've got three sort of cores here. Now these could relate to three separate weather events. In other words, during February, there were three strong wind periods when the wind direction was from either the north-northeast or from the west or from the north-northwest. Now that is not necessarily saying you wouldn't get ease from something in here if there was a jet stream in there or in here. But these directions do correlate pretty well with being downwind of the Cantabrian Mountains and the Pyrenees. So it'll be interesting, I think, to look at how these jet stream direction graphs and scatter plots correlate with, compare with different stations that don't have mountain ranges nearby. Anyway, something else to look at. So the contour change, whether the pattern's moving through quickly or not, doesn't seem to be showing a huge trend in February. Just got to re-emphasize that February is a really pants month. It's noisy, it's not got any strong triggers, it's just, well, it's got strong weather triggers, but it's not a renowned Sporadic-E month. So there's a lot of shash going on in here, which doesn't really help my case, but I've decided to come clean and just, this is what we've got. So surface wind, doesn't seem to be a lot to go on there. The LROD index I'll introduce as an all-in-one turbulence parameter that was developed in America for forecasting clear air turbulence for aircraft aviation, that sort of thing, and it's a meteorological thing, and there are other parameters which I'm going to move on to next and compare them and see which one might figure. So it'll allow us to combine, you know, the contour changes and the vorticity and jet stream strength into one parameter, which will make it easier to deal with. And this one is the height of the FOEs going on there. So then I thought, well, let's have a look at this, which is seeing if the velocity of the jet stream has any bearing on which bands open and the direction. So up here on the y-axis, we've got the velocity at 300 hectopascals. Hectopascals, by the way, in case you haven't realized what they are, they're the same as millibars. Numerically, it's the same as me writing a 300 millibar chart. but this is the way we do it nowadays. So it's 300 hectopascals after Monsieur Pascal. So here we go. The direction shows the same, but here you can see there would appear not to be any great favoritism of a wind direction here for any given band. So we've only got less than 10 meters ease and 10 meters up to 6 meters, but not quite making 6 meters here. So that will be an interesting one to see as the season develops. Here's one that I did using that previous one, by the way, it was just an on the hour mix. This one is using the highest one within the hour following, and it does allow us to get a 6 meter one in, and it's putting vorticity up the y-axis, positive at the top, negative vorticity. So this is anticyclonic, upper ridges. The top half is cyclonic, so it's upper lows. And then contour change, the bottom left is falling contours. So this is contours reducing as a trough comes in. And the right-hand side on the x-axis is contours increasing as an upper ridge develops. So positive vorticity, low pressure, falling contours. We'd expect over time, not just looking at February, to see this pattern extending up here. And similarly for ridges and upper highs, we'd see it coming down here. So what interests me now is whether when we get a whole year's worth of data, we start to see brighter colors from higher bands moving away from the center down that axis. But it'll be, an interesting little insight if we can get it to do that. And then I thought, well, let's have a look at this and see what percentage, and it's just developing it for the future months. So I'll look at this on a month by month basis and look at it for the different sites, and we can see what percentage meets those thresholds, more for an amateur radio operating guide as anything else. Now let me just move my people off here so I can talk about this one. This was just a bit of fun at the moment to look at the number of occasions in the month when I'd gone for an EPI of less than 50, so more likely not to get ease than get it, and we do see a slight favoritism towards no ease than ease. When you get up to that period of EPI, that interval between 50 and 75, we do end up with more ease than no ease, so that's good. And for the highest value, it's quite strongly on the one side, a small sample. So you're going to say, well, there's not enough here to go on, which of course is true, but it shows that we've got something now ready that we can put together to say to do a little quick sort of test of how effective this thing is working. Right, now this one takes perhaps a little bit of explain. I'll have to speed up a bit more. Looking at the month overall, the background colors suggest those approximate bands. The spikes on the bottom are the FOEs. So when it's in blue, it reaches 10 meters. When it's in this yellow color here and here, only 2, it reaches 6 meters. When it's in gray, it doesn't reach one of the amateur, well, it's obviously on the lower HF bands, but doesn't get up to 10 meters. And then the lower graph is the EPI, and you'll see we went very strongly for this one. For this one, it was also a similar pattern to that one, so I haven't looked at that closely. This is interesting because it's a strong return from the FOEs on the ionoson to 6 meters, and yet was very underplayed, a bit sort of for that one. So the EPI wasn't very enthusiastic there. And then case C I thought I'd put in, because that's got nothing in it at all. Out of the whole month, which normally you wouldn't expect much anyway, it's bereft of activity, and also the EPI wasn't keen. So let's have a look and see. So the first one here, this was a northerly jet stream. I briefly spoke about these maps where the yellow is above 100 knots and so on. And here we've got the Pyrenees across the north of Spain and a strong flow on the edge of it, lots of vorticity probably. And B, it's an upper trough coming through. So these faint black lines here go down here and then up there. So there's an upper trough coming through there, and then rising contours behind it. And C, with nothing going on the upper air chart, an upper high. So in other words, The one that produced no results was on the middle of what would be an upper ridge if it wasn't moving. It's a static bit of the atmosphere through the depth of the atmosphere, not much going on aloft to generate anything. So there's no flow. So a gravity wave wouldn't be happy in that place. So this is a plot I've developed to look at more closely during the season. The purple line here is the vorticity. That was all negative in Class A because we were on the western side of the jet stream. Contour heights rising slightly, this blue line here, and the red bar chart is the LROD index. The ease probability index followed broadly the period when we had FOEs, these green bars. But the peak that I went for wasn't really a peak, although it did crop up here. And it'll be interesting to see what actually drives these periods. It could be that we need to get into this plot something about the tidal window, semi-diurnal tidal window as well. But the other thing I thought I'd mention, because we're looking at weather parameters to try and resolve this issue, the jet stream's threshold of 60 knots along the bottom here, the wind direction is almost exactly northerly all the way through. So when you look at that plotted, you have a very strong showing descending node, and it sort of peaks up here at about 7 megs. So a good case for 6 meters ease just on there. But is it best, is it sufficient to put in a single descending node, or can we break it up into different components? So this bit here correlates with these periods here. In the morning period, then we get the main bit of the morning descent going on here. Then we get a period here, which is the evening period in grey, and this on the timeline you'll see down below here is the grey zone, which is probably a bit what's left of the diurnal tide. But even that we can split up this second part of the day. So there's a lot of interest in here in determining which bits belong to weather and which bits are just semi-diurnal tide, and what can we use from this to get some predictive skills. So here's the satellite picture, a lot of cloud blocked by the Pyrenees. Could be a physical block with the inversion stopping the cloud going, or it could be a mountain wave that descends on the other side and the cloud evaporates. So case B, which we didn't predict, you'll see our EPI line here failed to get even up to 50%, reasonable ease, strong enough to get to 6 meters, but some good response from the LROD index. So there's some promise there that we need to have a look at that, and some positive vorticity going on. But the jet stream strength, which is why the index didn't do well, decreased during the period. So I've obviously got too much influence exerted from the strength of the jet stream compared to some of the other parameters. And again, if you look at it, we've got a nice descending node. So having this descending node seems to be a key part of all this. And then here's the satellite picture, and it shows that on this occasion, in fact, we had a southerly wind. So there was a parallel line of cloud to the north of the Pyrenees. So that's something which we'll continue to look at. Now, case C, I'm just on the last slide here pretty much. So case C, well, no change in contour heights, this blue line running along the center here. So contour change, none, pretty much. Vorticity, strongly negative. So this is a strongly negative vorticity trace. So there's no positive cyclonic vorticity, but there's strong negative vorticity, which is anticyclonic, the upper high where we had the high pressure, and just 3 or 4 random blips of FOEs. So the forecast was correct because we didn't. The EPI got onto it. The speed of the jet stream is way below the 60 knot line here, this purple line, and the direction didn't change much, but it's a case of nobody got enthusiastic about this because the winds were light, the flow was not being affected by mountain ranges, and the only thing we have to play with here is a strong negative vorticity. And the cross section from the ionosons just came up with a token thing here. Question might be, what caused that? We can't see the descending node up here because there was not enough ionization for the ionoson to pick up. But is this still being affected in the same way, or was this just a random meteor thing? Completely sunny skies there, except for a bit of snow and the odd cloud over the Pyrenees themselves. So what next? Add more work, more parameters to the investigation. So I'm going to put in the SFI, the K index, thunderstorms, other turbulence indices. I'll be upgrading the EPI in response of all this feedback from these different parameters. When we get enough data, and we had a very interesting talk on the statistics of analysing things yesterday, I shall be bringing the heavy guns in and talking to people who know about this stuff. And I do think it's really important to get some real-time meteor data put in here. And the ideal thing for me going forwards is to put some of this graphical material online as part of the PropQuest website. So that's it. I'm sorry I've overrun slightly. I'm really grateful for the opportunity to do it. Big thanks to all those who've helped, and particularly the many amateurs whose logs make all this study possible. Lowell Digisons, brilliant resource for me, DX Maps and all the other online clusters, and my chums at work, Dan Holly and WeatherQuest, for supporting the site. So thank you all, and sorry I've pinched some time.
Thank you so much, Jim. That was wonderful. Very fascinating. And it's great to see all of your work connecting the neutral atmosphere with something that, radio amateurs can really appreciate. Are there any questions? There's a question on Zoom. Phil, you're a panelist, so you can actually speak directly.
I am. Hello, Jim, from this side of the pond. That's really, really nice work, as we've seen before. This is just maybe a clarification for this audience. And I put this in the chat in that, meteorologists work in pressure levels. And a lot of times when you see ionosphere stuff, you see it in altitude levels. So it might be useful just to let people know, when you're talking about 300 hectopascals, if you were able to translate that to an altitude, and I know that's complicated, kind of where are they? It helps, I think, people sort out where the gravity waves are and where the ionosphere are.
Well, the 300 millibar level goes back a long way in meteorology. It's roughly about 30,000 feet or so in round figures, so 10 kilometers or so. It's a height where jet streams operate. They're a sort of an ellipse of strong winds. If you look at it sidewards on, it's like a tube of strong winds, and it exists across a broad height range at that sort of level. And the trick is picking a value of a pressure surface where you capture the best chance of seeing where the maximum winds are and picking up a jet stream. If the jet stream is below that level, you might not see its full impact. So bear in mind that a 300 millibar is a proxy for the approximate location of a jet stream. And it's been the one that's sort of standard in meteorology. When Concorde was flying, they used much higher pressure level charts for those forecasts. And before we got into the jet flight and it was prop engines, the upper level that meteorologists played with was 500 millibars, and that's about 18,000 feet. But the jet stream one tends to be 300 millibars, and that's the one I've stuck to just for consistency.
Yeah, thanks very much.
All right, thank you. I'll take one more question, actually maybe two more. So, got microphones going around. Veronica, maybe you can go back there to him.
Yeah, I have a question and a comment. The question is about, you mentioned meteors a few times there, and I'm just curious what your thoughts are on correlation with meteor showers. And just a comment along those lines is something to think about for that is that meteors, depending on their speed, ablate at different altitudes. And you mentioned the Leonids, those are the fastest. They're about 72 kilometers per second. So their ablation altitudes are higher than, say, the Geminids would be at 35 kilometers per second. So that might kind of figure into the mix as you dig deeper into that. But I just wondered what your thoughts are.
That's a very good question. I mean, I think one of the things that goes back to the red sky at night, shepherd's delight part of Sporadic-E forecasting was that amateurs tended to always book the first week of June off for their holidays to operate Sporadic-E, because it was a combination of several smallish meteor showers. The thing that became apparent to me, and that's a really good point about the meteor showers are different, that there isn't just one standard classic meteor. And when I did an article recently in Radcom Plus, I don't have the reference to it here, but it was last year, for that exercise, I looked at the meteors and came up with a quantification based on the speed of the meteors, the number of them per hour, as to how important a meteor shower would be. I didn't look at the height part of it, which is a really good point. And it turned out there are 4 major meteor showers in the year which are more important than the others, simply because of the size of the speed of the meteors, the number of them you get in the period of the shower. So that was a way of saying perhaps we need to focus not on the meteor shower, but on the actual input, the volume of content coming in to the E region as these things burn up. But I'd be very keen to talk to people more about different ways of fine-tuning this, because that's one of the next things. The other thing I mentioned briefly along the way was this background meteor input figure, which came from a paper a few years ago now, but it came up with a graph of meteor input by day through the year, and that was a very illuminating thing. And if you took an arbitrary threshold in that, you will find that this background meteor input correlated very well with the seasons of Sporadic-E. So I think we've got a very good pointer to looking at meteors with a magnifying glass for this. So thank you for that point about the speed variation and the consequence on the height at which they burn up.
Thank you. Last question.
I wanted to know if you had used SCUT log P charts, which come from wind radiosondes and commercial pilots use.
Yes, I have. I mean, in Europe or in this country, we tend to use T-figrams, which is a similar thing to a SCUT, but the same sort of these aerodynamic charts, and they do contain properties which describe the wind regime with height, and in some of those, you can clearly see the occasions when there is wind veer, and the thing about the gravity wave business is that as you go up in height, the wind changes direction, and when you get a good signal for that, it's indicative of gravity wave activity. So that's another resource to put into. The slight problem we have with that is a bit like the amateur logs being widespread and the ionosondes being focused, is that the launch balloon sites are very isolated and not necessarily where an ionosonde is. So it becomes more of a generic thing. But I have written about that in 1 or 2 other articles, and it is a very rich vein of resource for looking for parameters like the LROD index, but similar ones that predict clear air turbulence and so on, based on just that sort of thing.
Thank you very much. I really appreciate it. And now, stand by. Let's see. Yes.
Oh, I've got to stop sharing, haven't I?
And now I would like to virtually present to you a certificate of appreciation from the HamSCI community for your invited tutorial. So thank you. And we will be mailing you a copy. What's up?
It was a pleasure. Thoroughly enjoyed being here.
Thank you. And we will be sending you a signed copy of the certificate and a special HamSCI coffee mug, or I guess maybe for you a tea mug, that you can use for the future. So thank you so much, Jim.
My pleasure. Thank you.